طيب بسم الله الرحمن الرحيم. So last time we talked about the diffusion update algorithm as part of the EIGRP, and we said that this algorithm is used to find the loop-free path for a particular destination network. So today we're going to discuss the terminology of this dual algorithm and how EIGRP uses this algorithm to find the loop-free path. So dual provides the loop-free path and provides a backup path. What is the definition of a backup path? The backup path is a path that's in normal condition, it's not used. So it's used only when there is a problem with the primary path. Okay? Which is different from the concept of load balancing that we have discussed before. So we said that RIP and EIGRP actually, they use load balancing. So if the cost of two routes is the same, then we actually insert both of them in the routing table, and they are used concurrently if they have the same price, if they have the same cost. Backup path is different. Backup path means that you have one primary path which is used in normal conditions. If this primary path has any problem, for example, there is a network change that makes this path not valid anymore, okay, then you bring the backup path, one of the backup paths from the cache, and then you insert it in the routing table in replacement of the primary path. فهمنا فرق؟ That's the concept of the backup path. Of course, because dual update algorithm uses is based on the triggered updates, and as we said before, if we try to get to a destination network that we don't have any route in the routing table, then we use the concept of searching for this destination network. So we send a request or a query request. This is what we have talked about last time. We send query to all the neighboring routers to search for this destination network. And when we get the reply, then we apply the dual algorithm to try to find what is the primary path. The primary path basically is the path with the best cost at this point in time. Okay? But there are some other paths that might have more cost. So they are not the best path. So in that case, dual algorithm checks that these paths, this secondary path or backup path, these are loop-free. If they are loop-free, then dual algorithm keeps this path in a cache as backup path. So if the primary path is failing, then we bring one from the backup path and put it in the routing table. Okay, so that's how it works. So the dual algorithm uses some terminology. The first one is the successor, and the successor is the next hop. Okay, so for example here, EIGRP uses the successor is the next hop, which is the 192.168.10.10, which is the next hop for this destination network, which is 192.168.1.0. So any destination address on this network, we use this successor. Okay, and the cost would be this. And as we said, the cost is large value. Okay, so the successor is the best least cost route. This is the successor. And this successor has a feasible distance, which is the cost, which is the minimum cost. Yeah. Okay, so this is the terminology that dual uses to find the primary path and all the backup paths. Okay, so this is the next hop for the best route, and this is the feasible distance, which is the lowest calculated metric along a path to a particular destination network. That's easy. And there is the feasible successor. A feasible successor is another next hop. okay, that can get you to the same destination, but with slightly more cost. But a feasible successor here achieves two conditions. There are two conditions here based on which we say that this is a feasible successor. One is that this successor leads to a loop-free path. As we said, this is a condition. If it may cause some loops, then we don't consider it as a feasible successor. The other one is that it fulfills what we call a feasibility condition, which we will talk about in a minute. Okay, so this feasible successor is another next hub that will get you to the destination network with two conditions. One is that it will lead to a loop-free route. The other thing is that, of course, because its cost is more, it's not considered as a successor or the best next hub, but it can be considered as a backup route. And for it to be considered as a backup route, it has to fulfill the feasibility condition, which we'll talk about in a second. Okay. In order to talk about this feasibility condition, we have to define something which is called reported distance. And the reported distance is the distance that a router reports to another router, okay? So for example, a router here has a cost to this network, which is this cost. So this router, in order to reach to this network, it has this cost, okay? But R1 reports to R2 a distance to the same destination network, which is this one, okay? In normal condition, R2 will go through R3 to reach this destination network. Of course, it can go along this long route, but it will not. It will use R3 as the successor, because R3 is the successor with the lowest cost at this point in time. However, R1 here has a reported distance, which is in the routing table of R1, it's the feasible distance to the same destination network. So if we look at the routing table of R1, we find that in order for R1 to go to this destination network, it will use this feasible distance because it has to go through R3. Okay? When R1 uses this distance and reports it to R2, we call this as a reported distance, which is different from the feasible distance that R2 uses. So R2 has a feasible distance to this destination network, and it may receive a reported distance from R1 about the distance that R1 uses to reach to the same destination network. This is what we call reported distance. Why do we need to use the reported distance with the feasible distance? Is the feasibility condition talks about the fact that this reported distance from any router has to be less than the feasible distance to the same destination network. Okay? Remember that, I mean, if this is less than this, so why don't we say that, okay, this is the feasible distance to this destination network? Because it's not. From R2 perspective, it has to go through this link first before it can use this distance as a feasible distance, right? And this link still adds some cost. So when you add the link of this cost to the reported distance, then of course the total cost will become more than this cost. And that's why we cannot use it as a feasible distance from R2's perspective, right? But the feasibility condition talks about the fact that this reported distance, it needs to be less than this feasible distance to the same destination network. Then and only then we can use this route as a backup route. Okay, that's what we the feasibility condition. So the feasibility condition is met when the neighbor's reported distance is less than the local router's feasible distance to the same destination network. Okay? So that's the feasibility condition. So that indicates that the route should be loop-free, and the reported distance for this backup route, which means that the reported distance from the neighboring router should be less than the feasible distance to the same destination network. This is the feasibility condition based on which we can keep this backup route in the cache and maintain it in the cache. If there is any failure, if there is any network change that affects the primary path, then and only then we can replace this primary path with one of the backup paths in the cache. Any question? So that's basically what we need to discuss for, of course, the dual algorithm is complicated, and luckily we don't have to get into the details of how it actually calculates this feasible distance and reported distance and all of this and compare and so on, based on which we put it in the cache, based on which we put it in the primary routing table and so on. So we don't have to get into the details of this, but we'll stop the discussion at this point. So we switch to the last topic, which is the Linkstate routing protocols. As we said, largely and generally, Linkstate routing protocols, they are aware of the global topology of the network. They don't use distance and direction, okay? And they work based on the shortest path, end to end, which means that from any point to any point, you have the whole topology, you have the cost on each individual link, so you can construct the end-to-end shortest path from any point to any point, because you know all the information. Okay? In this category, we have two protocols. One is called intermediate system routing, and we have OSPF. OSPF has version 2 and version 3. And we will actually discuss the details of OSPF only, because it's the most common. These routing protocols, they use the algorithm that's called Dijkstra algorithm. Dijkstra algorithm is the algorithm that's used to identify the shortest path. Because the routing protocol is used to collect all the link states or all the costs of the individual links in the entire network. Okay? And then Dijkstra algorithm will run from any point, from any router, and start constructing the minimum path to all the other points. So starting from one point, we construct, because we know all the information, so we go from one point, and then we try to construct the shortest path to all the other points, because we know the state of all links, and we'll see how. So Dijkstra algorithm is the algorithm that's used. For the distant vector routing protocols, there is a similar algorithm that works a little bit differently, of course, because it works more efficiently with the concept of distance and direction, which is called Bellman-Ford. So that the distant vector routing protocols, they use the what we call Bellman-Ford algorithm. And Bellman-Ford uses the concept of, if I have some distances coming from all the neighboring routers, then I work greedily. So what is the best route to a particular destination network? Well, basically, I get some distances from all the neighboring routers, so I select the minimum. Okay, so the minimum one to a particular destination network, this is the one that I should use in the routing table. Okay, that's basically how Bellman-Ford works. It's a greedy algorithm, and it's simple. It gets all the costs that are reported in the message updates or in the route update messages, and then it selects or it puts in the routing table the one with the minimum cost. Dijkstra algorithm it works a little bit differently, which we will talk about in a minute. So the way Dijkstra algorithm works is that, well, we have all the costs for all the links. So from R2, for example, to this destination network, we know that this link has a cost of 20. This LAN has a cost of 2, and we'll talk about how you actually calculate this based on the bandwidth of each link. Okay, and this link has a cost of 5, and so on. So if I want to go from this point to this destination network, what is the best path? Well, we can go this way, we can go this way, or we can go this way. So basically, I add all the costs associated to each individual path, and then I select the one with the minimum cost. It's very easy. So it's obvious that this cost, for example, is the total cost is 27. The total cost here is 20 plus 20 plus 10, which is 50, plus 2 actually, which is 52. And if I go this way, it will be 10, 10, 10, 2. So it's 32. So basically, this one, 27 is the minimum. It's as easy as that. Okay? So this is what we call the shortest path first. Shortest path first algorithm, which is what we call Dijkstra algorithm. Of course, the way Dijkstra works is that from one point, what it does is that it says, okay, I can go this way, or I can go this way to a particular destination network. So the minimum cost in that case is this. Okay? But I have to keep this in my table or in my cache. So from here, I can get to here only. Okay? So the total cost is 20. Okay? Then I go here. And then I say, from here, I can get here, or I can get here. Which one I should select? Well, the one with the minimum cost. So I go this way. And then from here, I have to construct. I can go here, and I can go here. So every time I keep traveling to a different direction, and I keep only the one with the minimum accumulated cost. So I construct what we call shortest path tree. So from one point, okay, how I can reach to all the other points. For example, the shortest path tree from R2 would be, first R2 needs to go to R1. Well, it has only one path. From R2, I need to go to this destination network. So there is only one path. But R2 needs to go to this. Well, I can go this way, I can go this way, or I can go this way. So if I want to go to this, I have to go to this through this path. Okay? If I want to go to R4, well, I can go this way or I can go this way. But I will keep only the one with the minimum distance, which is this one in that case. Okay? So in that case, I have a shortest path tree, which is like, this is R2. And then if I want to go to R1, I have to take R2, R1 path. And then when I go to, for example, R4, then I have to go to R2, R5 path, right? So from R2 to R4, I can go this way or I can go this way. But I will keep only one, because it's a tree. I can keep only one with the minimum distance, which is in that case, R2, R5. Through R2, R5, I can reach R4 with the minimum cost. So that's the path that I will select. R2, R5, and then R4. And I keep constructing the shortest path tree this way. Okay? So that's how Dijkstra algorithm actually works. You don't have to really, I will not ask you to write how Dijkstra work, or I will not ask you to write the code of Dijkstra, even though it's very easy. But but you don't have to really write down how Dijkstra actually is programmed. Okay? So the shortest path to a destination is not necessarily the path with the minimum number of hops, and we know that. So for example, if I want to reach to R4, I can go this way, or I can go this way, or I can go this way. Okay, so this one is 20. This one is 20 plus 5 plus 10 is 35, or this one is 40. So it happens that through R1, R3, from R, so the start point here is R1, sorry, not R2. The start point here is R3. So if I want to go from R1 to R4, okay, I can go directly to R4, or I can go to R3 and then R4. So it happens that the cost here is 20, the cost here is 15. So even though this is the longer path, but I will go this way because it's the minimum accumulated costs. Okay? طيب, how do I facilitate the main job of the routing protocol is to get me to a state that I know all the costs on all the links at every router. Okay? Once I know that, then I can apply the Dijkstra algorithm to construct, from every single router, to construct the shortest path tree to all the possible destinations. Okay? So the purpose of any link state routing protocol, for example, OSPF, is to convey the costs on all links and make all routers aware of the cost of every single link in the network. Okay, so once we do that, we have like a link state table. We apply Dijkstra algorithm on the link state table. We construct the shortest path tree to all the possible destinations, and then from the shortest path tree, we get the routes and we put it in the routing table for packet forwarding. That's in a nutshell how the link state routing protocols work, which is different from distant vector routing protocols. We don't have link state table. We don't have shortest path tree. Okay, we have directly the routing table, which can be constructed using this accumulated distance that are reported from the neighboring routes, from the neighboring routers. So how do we start the link state routing? Well, this step is somewhat similar to the distant vector routing protocol. Each router, when it first starts, through these interfaces, it knows exactly all the directed networks, right? So it forms what we say the link state of all the directly connected networks. So we know that. We don't have to wait for someone to tell us any information about the networks that are directly connected to me. I can know that directly from the interface. Okay? So router 1, for example, has 1, 2, 3, 4 directly connected networks, right? So it collects the information about every single network in such a way that, I know the destination network address, and then I know the type of the network. If it's Ethernet, I know the bandwidth, and from the bandwidth, we'll see how I can calculate the cost of this directly connected network. So all this information is given. Okay, so I start with that. So from each link, I actually calculate what we call the link state. The link state is the information about the state of the link. The link is active and the link has a bandwidth of X, which means that the cost of this destination network is Y. And we'll know how to calculate the cost. So this is the first step. The second step, okay, before I start exchanging any link state information, I have to know who are the neighbors. Okay? Similar to EIGRP, OSPF again uses triggered updates or triggered link state updates. Okay? So in that case, we have to have a prior step so that we become aware of all our neighbors. For example, router 1 does not have any neighbor along this interface. It does not have a neighbor along this interface. It has a neighbor here, it has a neighbor here, and it has a neighbor here. But it does not have a neighbor on this interface because this is a LAN. This is a LAN interface. So in order for me to become aware of all the neighbors, I have to exchange some hello packets. Again, similar to the case of EIGRP. The only exception that we have studied in this part is a RIP. RIP does not use hello packets because it uses a... Why doesn't RIP use the hello packets? Because it uses periodic updates. Periodic updates are implicitly used to exchange information about the neighbors. Because as long as I'm getting some periodic updates from someone, he is my neighbor. But here, we may actually keep working for like an hour with no changes in the network. So how would I know that my neighbor is down? Or I don't have a neighbor on this side? How would I know that? Well, for RIP, I know that from the periodic updates. Because regardless of whether the network has conversions or not, I have to keep receiving periodic updates from all my neighbors. So I don't need to exchange hello packets. But here, because the updates are by default triggered or event-based, then I need someone to tell me who are my neighbors. Who are my neighbors, okay? So I have to send hello packets between all the routers. And remember that hello packets are by default are sent using multicast or broadcast along all the interfaces, okay, to all the which reaches to all the neighbors, and then when the neighbors send me back some acknowledgement, then R1 indicates to R2 that I'm alive. When R2 sends hello packets to R1, then R1 knows that I have a neighbor who is R2 and he's alive. And similar again to EIGRP, if I don't receive this hello packet for quite some time, we'll talk about how much, then we recognize that R2, for example, has gone down. Then I have to remove it from the adjacency information. So each router, when it receives hello packets, it forms adjacency information. So R1 knows that it has some adjacent node, which is R2. It has some adjacent node, which is R3, which is along this interface. And it has an adjacent node of R4 along this interface. And it has no neighbors along this interface. Okay? So the purpose of this hello protocol is to discover the neighbors that use the same link state routing protocol. And this point is important now, because who is my neighbor? My neighbor is the one connected to me physically, and he or she is using the same routing protocol with the same process ID that I'm using. If the router 2, for example, is using a different routing protocol or is running a process with a routing protocol with a different process ID, then it's not a neighbor to me. Okay? Only when I can exchange some routing information. In order for me to exchange routing information, then this router has to be physically connected, and it has to have the same routing protocol, and it has to have the same process ID. Okay? Type. So again, the first step, we collect the link state of all the directly connected networks. Second step, we should recognize who the neighbors are through hello packets. And the hello packets is basically is sent as multicast to all interfaces, which is basically broadcast. Okay, all the connected interfaces that are using the same link state routing protocols will exchange hello packets. Because if I send a hello packet on this interface and this router is running a different routing protocol, it will not recognize this hello packet. If it's running the same routing protocol and it does not have the same process ID, again, it should not read this hello packet. Then this router will not know that this R1 is a neighbor. Type. Once router learns that it has neighbors, they form a layer adjacency. So we know that router 2 is an adjacent node along this interface. Router 3 is an adjacent node along this interface. Router 4 is an adjacent node along this interface. And along this interface, I do not have any adjacent node. That's how we form this information. So these packets will serve as keep alive function. Okay? Keep alive, which means that if I don't receive it for quite some time, I declare this router dead. Type. So this is again the second step, and it's very important. So first, I collect information about the the directly connected networks. Then I know who the neighbors are. The third step, now I'm ready to start exchanging information about the link states, including the cost and everything. Okay? Because I know who the neighbors are. I know all the information about the directly connected network, so I start sending the routing information. So this is the third step, which is each router builds a link state packet. The link state packet contains the information about the directly connected networks. Okay? And so the content of this link state packet is the state of each directly connected link, which includes the cost, and it includes all the information about the neighbor, as this link state packet should go to the neighbor, which is R2. So I specify that along the link state packet, the neighbor ID, the link type, which means that I have this link state packet, for example. So the link state packet contains all this information. So I have R1 has a directly connected network, which is Ethernet. R1 has a network which is point-to-point along the neighbor of R2, okay? And this network is a serial point-to-point, okay? Which means that it has, based on the bandwidth, we know that the cost of this link is 20. And along R3, I have point-to-point network with a cost of 5. Along R4, I have... So this is this information will be sent in one link state packet from R1 to all the... we'll see how it's sent. Okay? So this is the link state packet that R1 should form. So this is step number 3. Step number 4, this link state packets will be flooded in the network. And pay attention to this. It uses flooding, which is totally different from how you exchange the distances in distant vector routing protocols. In distant vector routing protocols, routing update or the message update is sent to the neighbors and it stops at the neighbor. And then each neighbor will have to process, get the information from the routing table, put it in another update message, send it to the neighbors only. Okay? Here, one link state packet will be flooded. Flooded here means that it propagates the same link state packet. It propagates to the entire area. And I say area, not autonomous system, which is we'll talk about in a second. So the link state packet will be propagated to all the entire area. Which means that it goes to, so R1, for example, will send a link state packet to R2, to R3, and to R4. R2 will get this link state packet and will forward it as is to R5. Okay? R5 will then forward the same link state packet to R4. Okay? That's how we mean by a flooding. Yeah, broadcast means that you have to send it to all your neighbors. That's broadcast. But flooding is a little bit different, because flooding, the same packet goes in all the network. Broadcast talks about one hub broadcast. So we send the message to R1, R2, R3, R4, and we send it along this destination network as well. That's broadcast, right? Flooding, it goes beyond that. When R2 receives this message, it will forward it. The same message will be forwarded, which means that you will have redundant packets being sent, okay? And each router will collect all the link state packets, will extract from it the link states of all the links, and will put it in the link state table. Okay? So this is the concept of flooding. Flooding is that you send the link state packet from one router, it has to propagate through the entire area. The same link state packet. Okay? So this is step number 4. Each router floods. This is the first time we use this keyword, floods, right? Which is slightly different from broadcast. Floods means that it has to go through the entire area. Okay, this is step number 4. Step number 5, each router will receive, of course, tons of these messages, okay, from all the other routers. So it will cache, it will store all these link state packets in the link state table. So for example, at this point in time, I received link state packet from this router, R3. So for example, R5 will receive a link state packet from R2, okay, which has some information about the directly connected networks, and maybe it's coming from R1, so it will have the directly connected ones from here, and it will receive also link state packet from R4 because it's flooding, so it will keep the information in this link state packet in the link state table. Of course, I will have to work out all the redundancy, the redundant information. I have to remove it. So if I collect two link state packets with redundant information about the same link, then I keep only one. Okay? But the idea is that by flooding, I make sure that all the routers, they have the cost of every individual link in the network, in the area. Okay? So this is step number 5. So this is how the link state table will look like. It's like a repository that I keep all the link state information from all the routers. Okay? This is the link state table. Then, in step number 6, I run the Dijkstra algorithm on this link state table to construct what I call the shortest path tree. Shortest path tree, it tells me that if I'm running this from R1 perspective, this is the link state table of R1. R1 will apply Dijkstra algorithm on this link state database, and it will come up with this. This is the shortest path tree. It says that if you want to go to R2, you have to go R1, R2 directly, and the cost will be 22. So if I want to go to R2, then R2 network, then the cost will be 22. Okay? If I want to go to R3 network, which is this one, then you go along R1, R3 with a cost of 7. If I want to go to R4, then I go R1, R3, R4, R1, R3, R4 with a cost of 17, and so on. This is what we call a shortest path tree. Of course, because it's a tree, I did not keep this path. I can go from R1 to R4 through this path directly. But I selected this one because it's the one with the minimum cost. That's the difference between shortest path tree and the network itself. The shortest path tree takes only one path from one point to an ultimate point. A network is in general like a graph, connected graph. Okay, so I want to construct a shortest path tree and remove all the branches that give me more cost than the one that I have. Okay. This is what we call shortest path tree. So I apply Dijkstra algorithm and building the portion of the shortest path tree. So the process begins by examining R2's link state packet. So the way that Dijkstra works is that it goes through each neighbor. So for example, R2, I have link state packet from R2 that gives me the information about all the directly connected links to R2. Of course, we know all of a sudden that one of this link state, I don't need it because I already have the information about this link, right? From R1's perspective, this network is directly connected network. So I don't need R2 to tell me the cost of this link because I already have it. So it goes through all this link state information through the link state packets, and it starts removing all the redundant information, and then it applies Dijkstra, which means that from R1 I go into a shortest path tree. So if I want to go to R2, this is the path. If I want to go to R4, for example, this is the path, and so on. So I start constructing the shortest path. So that's how I do it. So determining the shortest path tree to a particular destination, from one point to all the other point, I construct this shortest path tree table. Okay. Once the shortest path algorithm has determined the shortest path routes, these routes are now, remember I have the entire path. So for example, R1, if it wants to go to R4, okay, it has to go R3, R4. So in the shortest path tree, I have the entire path end to end. In the routing table, however, what do I need? In the routing table, I need the information that allows me to forward the packet in the proper direction. معايا? So from R1, if it wants to go to R4, in the routing table, all I need as information is that if I have a destination address of 10.8.0. anything, then I have to send it in this direction. Okay? So in the routing table has to match exactly what we have in the distant vector routing protocol. It's the same routing table, more or less. The information has to be the same at the end. But the methodology or the procedure that I took, or the approach that I took for the link state routing protocol is different. It's based on link state information and flooding and so on. But at the end, the routing table, ideally the routing table, if I run EIGRP on a network and I run OSPF on a network, the routing table should have the same information. Because they both try to reach the shortest path, but using different approach. So the approach is different, but the ultimate goal is the same. معايا? This is very important. So for distant vector routing protocol, does not have to keep track of link state database, shortest path tree, and all of this. It does not have to do that. Okay? But at the end, the routing table is is the same. So this is the routing table that at the end we know that these networks are directly connected networks and remote networks. If I want to go to 10.5.0.0, where's 10.5.0.0? Yeah, this one. So from R1, if I want to go to 10.5.0.0, I have to send a packet along this direction. So I specify only the next hop. That's it. If I want to know the entire path, then I go to the shortest path tree table to know that this packet should take this whole path end to end. It's similar to Google Maps. So Google Maps, in a local point, it tells you what, go to this direction, right? But in this point, if you are suspecting, if you are suspecting something, you can stop the car and say, no, I want to know the entire path end to end because I'm not sure if this information is really correct. So you can, in fact, ask Google Maps to give you the entire path, and then it's like you are jumping to the shortest path tree table, and then Google Maps will tell you, okay, if you go to this direction, then you are taking this route end to end. Then you go to this street, and then from this street you go to this roundabout, and this you go this and this and this. Distant vector routing protocols cannot give you this information in any circumstances. Meshi? This is the fundamental difference now. If you ask EIGRP at any point in time to give you the entire path, it will not be able to. It does not have this information. It has to ask the neighbor, if I give you this packet, how can you send it? Then it tells, okay, then it says, okay, if you give me this packet, I'll send it in this direction. Then it goes to the other router, and so on. But by default, one router does not have global information. This is a fundamental difference. Meshi? So from the shortest path tree table, we get the routing table. The routing table will only have destination network, next hop, and of course the total cost. Destination network, next hop, and the total cost. That's it. But it doesn't have the full information about the end-to-end path. Meshi? Of course, because of this, the Linkstate routing protocols, they have some characteristics. And one of these characteristics is the memory requirements. Obviously, as we can see, the minimum memory requirements for Linkstate routing protocol in general is more, right? Because we have to keep track of the entire path end to end, which means that we have Linkstate table, we have shortest path tree table, and then we have the routing table. So obviously, the amount of memory that we need is more, right? Processing requirements is also more because we have to deal with hello packets, we have to deal with Linkstate packets and Linkstate flooding, right? So all this we didn't have to deal with for the case of EIGRP, مثلا, or RIP, okay? So we didn't have to deal with that. Bandwidth requirements. Well, that's a tricky one now. Why? Because we said that, well, bandwidth requirements, I would say bandwidth requirements for RIP, it should be slightly more. Why? I mean, in terms of average bandwidth requirements. Why? Well, because RIP, even if the network is in convergence state, we still have and we must still exchange periodic updates, right? For EIGRP and for OSPF or Linkstate routing protocols, we don't have to do that. So we don't have to exchange route updates all the time. But what happens is that during startup, when the router first starts up, okay, it has to exchange and flood all the Linkstate packets in the entire network. So the initial bandwidth requirements for any link state routing protocol is even more than EIGRP. Why? Because of the concept of flooding. Right? Because of the concept of flooding. I have to flood the entire network with link state packets. Because my initial objective is just to collect all the link state information about the entire area. So at startup, it should be really, you see the bandwidth is going up. And by bandwidth here, we mean the bandwidth used to exchange route information, not the data bandwidth, right? So this is the bandwidth requirement for the routing protocol, not for the data. Okay, data is another story altogether. So at the beginning, each router will have to flood the link state packets. And then they reach to a state of convergence. What is the definition of the state of convergence for the link state routing protocol? Well, the state of convergence is reached when all the routers in the area, they have all the link state information of all the links in this area. Then they stop exchanging link state packets. Okay? And then they wait if there is a network change. So in that perspective, link state routing protocols, they are similar to EIGRP, okay? Because EIGRP, again, uses trigger-based updates, so it works only when there is a network change. The difference here is that link state packets are flooded, whereas for EIGRP, updates are broadcast to the next neighbors only. So the bandwidth requirement here tends to be more initially. But then EIGRP and any link state routing protocol like OSPF, again, they are in the same state. No requirement for exchanging anything until a network change happens. ماشي? So this is the characteristics, the general characteristics of any link state routing protocol. Now, we will study a specific link state routing protocol, which is OSPF. One example. Similar, for the case of distant vector routing protocol, we discussed two examples, RIP and EIGRP, right? Here we'll discuss only one, OSPF. So, similar to distant vector routing protocols, we take the same method of describing a routing protocol. We'll talk about the characteristics of OSPF, similar to IGRP. So the first thing we talk about is the message format. So the message format, again, we have data link layer frame header, we have IP header, and then we notice that we don't have a transport layer header. So OSPF, again, similar to EIGRP, uses its own transport layer method for exchanging the route information. So the header itself contains, of course, the version about the OSPF and stuff, and it has the router ID. So if a router is sending any routing related message, it should include its own route ID, and it should include area ID. So we'll talk about the concept of area. Area is a subset of we talked about the concept of autonomous system, right? Remember we talked about the autonomous system? OSPF tends to subdivide the autonomous system into areas based on geographical location. So we said that autonomous system is a group of routers that are owned or under the authority of a single entity, right? Area is, the definition of an area is that it's a subdivision of this autonomous system. So one autonomous system can be subdivided into multiple areas. Why do we do that? Because remember we talked about the concept of flooding for link state packets, which is unlike EIGRP, right? To limit the bandwidth requirement of exchanging these link state packets, we use the concept of area, which is a subdivision of autonomous system. Because if we flood the link state packets into the entire autonomous system, the bandwidth requirement for OSPF becomes huge. Huge. Because you're flooding into an entire network of, like, let's say, maybe 100 or 1,000 routers. It becomes huge, right? Because each router will take this message, will replicate it on all the interfaces. Each router will take the message and will send it on all interfaces. Then it becomes huge. By using the area, then each router should flood this link state packet within the area only. Okay, which limits the bandwidth requirement for exchanging this routing information. And then we will talk about the different message formats exactly similar to EIGRP. We had hello packets. We had also some hello packets in EIGRP, and we had برضو similar to this. We had a routing update message, and we had query and reply message, right? Here we have link state request, link state update, and link state acknowledgement, which you can relate them to. So the only weird thing that we didn't see anything corresponding to it for the case of EIGRP is what we call database description message. This looks alien to us. So we need to know how link state routing protocol like OSPF uses such a message. So the definition of all these message types is as follows. So we know the hello packet, which is used to discover neighbors and form adjacencies. So we know that. Anybody does not know that? So we're all familiar with the hello packets, right? It's broadcast to all the neighbors. ماشي? Let's jump here and we'll talk about this later. Link state request. Well, actually, let's talk about this. The database description message is used as follows. So a router will exchange link state packets with all the other routers, right? Will form the link state table. There is a chance that after removing all the redundancy and then forming the link state table, that some routers may be missing some link state about some of the links in the network. So when we flood these link state packets, each router will get this link state packet and will put it in the link state table. There is a chance that maybe a router may not have the link state information of one link in the network, in the area. Okay? So in that case, this router, in order for this router to know for sure that, okay, I have all the link state information that my neighbor has, okay, then what it does is that it sends a message which is called database description. The purpose of this message is like you are saying to your neighbor, I want to synchronize my link state database with you. I want to see which link state information I don't have, so that if I don't have link state information for one link, then I need to get it from you. But remember that the link state table could be huge. صح? It could be huge. Here in this message, I want to synchronize the whole link state table, which is huge. So what happens is that I don't send the entire link state table. I send only IDs of the links that I have. It's similar to مثلا when you fetch your emails using IMAP protocol. What do you do? IMAP gives you only the headings of the emails, right? So first you get the email, and then once you click on the email, then it goes to the server again and gives you the details, right? So similar to this concept, in the database description message, a router can ask another router or a router can give the brief information about all the links that it has link state information for. Then this router will compare what it has with this. If it finds that maybe one of the link state IDs, I don't have it in my link state table, then and only then it sends a particular request for this link. It says, I want to get the details of this link because I don't have it in my table. Okay? So the first step is that I get some brief information about the links that one router has. If I find that one particular link I don't have the information for, then I use link state request. Then I send the request to this router, telling this router, okay, I may have missed this link. Please give me the details about this link. And the details in that case is the link state information, including the cost and everything. Yaji? So I send the request, I receive the update message from this router with all the details about particular link or links, right? And then I send the acknowledgement. So that's basically how these messages are used. So first, I suspect that maybe I missed some of the link state information. I receive link state information in a form of database description. This is different from the link state packets. This is different from the link state packets. Link state packets are flooded, right? Then I get database description from a router telling me that I have these links. That's it. It's like a brief message. I have these links. Then, if some of the links are missing, then I send a link state request to this router, give me the details, and the router will give me the details in a form of link state update, or sometimes they call it link state advertisement. The link state advertisement or link state update will send specifically requested link state records. Specifically requested link state records with all the details. Okay? Then, of course, this is using reliable communication, so I have to reply with a link state acknowledgement to indicate that I received these link state records. Okay? Any questions? So, actually, we're doing good in terms of time, so I don't think we'll need more. So, in details, again, in terms of the messages that I send, we have the OSPF hello packet. So the purpose of the hello packet is to discover the OSPF neighbors. As we said, we discover the neighbors and form or establish all the adjacencies. And then we advertise the guidelines on which the routers must agree to become neighbors, which are, again, the fact that we have to use the same routing protocol, and we have to use the same process ID. And we add to that the fact that we have to be in the same area, right? Because if we're not in the same area, then I will not forward your link state packets, because we are in different areas. Okay? I will not forward your link state packet. So the link state packet gets flooded within the same area only. ماشي? Okay, so this concept is a little bit tricky now. So used for the case of multi-access networks, we should elect a designated router. We talked about the multi-access network last time when we talked about EIGRP. We said that if we have one switch and we have multiple routers connected to the same switch. So we have 1, 2, 3, 4, 5, 6, 7, and 8, let's say. This topology in particular forms what we call a physical star topology, logical mesh topology, which means that all these routers are connected logically with each other, right? So if I send a broadcast from this router, it will reach all the other routers, which means that all routers are neighbors to all. This particular topology is pretty interesting because when it comes to routing protocols, it forms like a bottleneck or a very interesting scenario that should be dealt with carefully, right? Because we are dealing with hello packets, okay, which uses broadcast. So, for example, if these routers, they send hello packet, then it goes from here to all the other routers. And then this router will send the same, which will reach to all the other routers. Which means that one message sent from one router leads in fact to assuming that we have n routers, leads to in fact to n-1 messages being sent on all the other links. Because we have n routers, so we have n messages times n-1. So this interesting topology can lead to n times n-1 messages broadcast. So in that case, dealing with hello packets, for example, becomes a real panic, a real pain. So if we remember for the case of EIGRP, we solved that using less frequent messages. So we said that in normal condition, we exchange hello packets every 5 seconds. But for the case of multi-access non-broadcast networks like this, we use the frequency of 60 seconds. So every 60 seconds, we send hello packets. So that was the solution from EIGRP's perspective. OSPF uses a slightly different approach. OSPF uses the concept of designated router. So the way this works is that every multi-access non-broadcast network like this, they will nominate only one router to become the designated router. Okay? So instead of the fact that everyone will broadcast to everyone, no. Everyone will send to one designated router only. And the designated router will then forward the message to others. So this way, I can reduce the number of messages from n times n-1 to basically n messages. Because I send one message to the designated router, and then the designated router will send it to n-1 routers. So it becomes n-1 plus 1, which is n. So I reduced it from this n squared order to n order. Okay? So this happens for the topology of multi-access non-broadcast networks. So that's a slightly different approach compared to EIGRP. Type. So OSPF packet header contains, as we said, the message type. And the message type here, we have 5 message types. We have the hello packets, we have database description, we have link state request, link state update, and link state acknowledgement. Okay? EIGRP used to have only 4, if you remember. We had the hello packets as well, and we had 3 messages for the route exchange messages. We had the query and reply, and we had the update message. So EIGRP has 4. Here we have 5 messages because we have one extra database description, which is used for synchronization between the link state tables of the neighboring routers. So the type will have the type of the message, and as we said, we have router ID and area ID. Again, area is a subdivision of an autonomous system which is used to exchange or to flood the link state packets. And then we have the OSPF payload, which could contain one of these 5 types of messages. This one gives you the details about the hello message. This one gives you the details about the hello messages. So in the hello messages, we should have the router dead interval. The dead interval corresponds to what in EIGRP? يلا بس عشان الناس تركز أو تستيميليت. صعبة. What do you think the dead interval is used for? For hello packets, I'm using a field called dead interval. What do you think this is used for?
No connection after to stop the router.
To stop the
Like the end of the router, no connection after the router.
No, I'm exchanging hello packets. Hello protocol now, right? Hello protocol is used to discover neighbors, right? So
there's no neighbor then.
if I don't receive hello packet after this dead interval, then we declare that our neighbor is dead, right? If you remember in EIGRP, there was a field that corresponds to this, which is what we called a hold time. I know it's a little bit hard because I didn't go through the material, but in EIGRP we used a similar concept using the hold time field. Again, in the hello packets, if you go in the message format of EIGRP, you will find a field called hold time, which works exactly as the dead interval. And the difference is very, very minor. So the hold time used to be 3 times the duration of the hello packets. Here, the dead interval is 4 times the hello packets. So if the hello packets are sent using, like for example, 10 seconds, which is the case of OSPF, then the dead interval is 40 seconds. For the case of EIGRP, the hello frequency was every 5 seconds. So the hold time is 30 seconds. So if I don't receive hello packets from the neighboring router for 30 seconds, then I declare this as a dead. Okay? And in the case of multicast non-broadcast networks, we have what we call designated router. Designated router is used to reduce the overhead of sending the hello packets within the same network. Okay? And we have backup designated router. Backup, again, the concept of backup means what? In normal conditions, I don't use it. Only if the designated router is dead, then I use the backup designated router, right? So I don't use both of them at the same time. Only a backup means what? Means in normal condition, I'm not in the picture. Only when the designated router becomes dead, then the backup designated router becomes into the picture.
How do they select the designated router?
Bravo, Ali. This is a very good question here. There is an election process. They have to elect. Yeah, democracy, it's all about democracy. Routers, they have to elect. The election process is out of the scope of the discussion, but basically they exchange messages with each other, and then based on certain criteria that, for example, مثلا, the one that has the minimum round trip time مثلا, will be the designated router. So they have to have an election process prior to that, and then they say, okay, router X is the designated router. And the second best would be the backup designated router. Any other question? Questions tell me that you're still awake, yani. Okay, so we'll stop here. We have a few slides that we can talk about after the quiz next time, inshallah.